What's up, everybody? Back for some more. All right. Well, we are in week 4 of our quarantine classroom instruction. Uh, and I hope you guys are doing well. We only have 6 weeks left. I know that 6 weeks of online instruction seems like a lot. But if somebody said you only have 6 weeks of school left, you'd be like, oh my gosh, it's almost summertime. So even though it doesn't feel like summer outside, it's almost summer. So here we go. We're going to kind of move into our gas laws unit. We did phase changes last week, and I think that I was going to start just by going into Boyle's Law, but I think it's important that we spend a week just talking about the variables. So this week's going to be pretty easy. There's going to be some things that you haven't heard of before, and that's okay. Because ultimately, I just want you to understand what the different variables are that impact gases, because that's what we're going to start talking about. And in about 4 weeks, I have the best assignment ever for you. Your assignment for the week is going to be to watch a movie, but we got some work to do before we get to that point. So, all right. So I'm doing screencast. You guys can see my screen here. This is not going to be an exceptionally long one because it's not a lot of material. I threw some extra videos up there that I think kind of touch on some of the things pretty well. They're short. One's like a minute, the other 2 or 3 minutes, so have at it. All right. So we're ultimately going to start talking about gases, right? And gases are impacted by basically 4 variables. Okay, you have your volume, you have your pressure, you have your temperature, and then you also have what are called moles. And that's a really fancy way of saying the number of atoms that we have present. Okay, so think about a basketball. If you left a basketball outside in the winter, it would obviously deflate. It would not bounce nearly as high. And there's a couple of reasons for that. The main reason that's impacted is because of temperature, right? As temperature decreases, the pressure decreases. So we're going to talk a lot about that going forward the next couple of weeks, how these variables interact. But what I want to do this week is just talk about the variables, okay? So the first thing we've got, let me see if I can turn on my cursor here. No, oh well. All right, so the first thing we got is volume. We've talked about volume 10 different times this year. Volume is simply the amount of space something takes up, right? So if you have a basketball, or let me go to my props here, you have a baseball, the volume would be the amount of space that this baseball takes up, okay? And you could measure that in milliliters and liters. And how would we do that? We would have to get a really big graduated cylinder, okay, a wide mouth, and we would take the baseball, we'd get the measure of the water, say it was 100 milliliters, we'd put the baseball in the water, and the water would obviously go up. Suppose it went up to 150 milliliters. The volume of this ball would be 50 milliliters. The amount of space it takes up, that is the volume, okay? Now, pressure is something that you guys have certainly heard of before, whether it's peer pressure or pressure in a science class or applying pressure to something that you're gluing or whatever, okay? So think about peer pressure. Peer pressure is when somebody tries to force you to do something that you don't want to do, okay? Pressure, for what we're talking about, is another kind of force. It's basically the amount of force being exerted per unit of area. And what that means is how much force is being exerted in a given area. All right. And we measure that with a couple different units. We have atmospheres, ATM. Okay. The standard unit for atmospheres is 1 because we live on Earth and there is 1 atmosphere. So the amount of pressure that atmosphere exerts is 1 atmosphere. Okay. If you measure it there. Some other ways you can measure it is in PSI, which is pounds per square inch. You may have heard that if any of you drive or ride a bike, you have to fill up your bike tire and you'd need to have a certain, it's usually 35 for car tires and somewhere between 40 and 60 for bike tires. If it's a road bike, it's probably upwards of 100 PSI. Now, that's basically pounds per square inch. So on every square inch of a surface, there's 14.7 pounds being pushed down on you. So that means, and if we were in school, I would have this really long black metal bar that I would take around and I would hold it up, and on the bottom it would be 1 inch by 1 inch, and you would hold it, and that bar weighs 14.7 pounds. So on every inch of your body, you have 14.7 pounds of pressure pushing down on you. And you're probably saying, Whoa, no way, that would crush me. And yes, you are correct, that would crush you. But you also have that amount of pressure pushing back, therefore, you don't feel it. Now, if we were to remove some of that pressure pushing back, you'd feel it. And so one of the demos I'm going to do for our lab is I'm going to put somebody in a garbage bag and I'm going to suck the air out of that bag. Now, if we were in school, I would do that to one of you, but I can't since we're not there. So anyway, all right. The other one is kilopascals. That is the metric way to measure pressure. We're not going to talk a lot about that. And then you have torr and millimeters of mercury, right? And so without going into too much detail, basically that's the amount of pressure that is exerted in our atmosphere. So if you had a barometer, which is a tool that measures pressure, and you set it up, it would measure it, and the atmospheric pressure would push the mercury up a tube 760 millimeters. I don't want to get too much into that. And the reason you have torr is a guy who discovered that was a guy named Torricelli back in Italy in, I think, the 1600s. Okay. So anyway, so these are the standard units of pressure. So these are all equal. So 1 atmosphere equals 14.7 psi equals 760 torr equals 760 millimeters of mercury equals 101.3 kPa. That is simply just like saying 1 foot equals 12 inches. The units are interchangeable. They're just different units, right? Okay. What do I want you to know from this? Basically that these are your standard units of pressure right here, okay? And that a force being exerted is pressure. Pressure is the amount of force being exerted, okay? All right, temperature. You guys know temperature. We've talked about it. Temperature basically is how hot or cold something is, but we did talk about, really it's a measure of kinetic energy. How fast are your molecules moving? The faster something moves, the hotter it is, right? Think about when you put something in a microwave. You are basically sending radio waves through that, and it's speeding up the molecules, thus making your food hotter, okay? If you boil water, the faster those molecules move, the hotter the water feels. So temperature is simply a measure of kinetic energy, okay? Our units. In the United States, we use Fahrenheit. Why? I don't know, because we're weird, and it doesn't make any sense. What temperature does water freeze at in Fahrenheit? 32. What temperature does it boil at? 212. Odd numbers. For Celsius, it's 0 and 100. It makes sense. And then we've got this new guy, Kelvin, okay? And so think about a gas gauge on a car. If you had a gas gauge and it was at 0, do you have any gas left if it's on E? Now I know you're saying, I can go 25 miles when it's on E. Like, I know, but let's go theoretically here. So if you have no gas left in your car, it's on E, you have nothing left. Whereas temperature, if you have 0 degrees Celsius, can you still walk outside? Yes, right? So there's still energy present. You can still move. It's just really cold. Could you move at -10? Yes, you can't have -10 gallons of gas in your car. It's not possible. That's not a thing. But it can be -10 degrees. And so what you have is, if you take that absence of energy, that absence of movement, that is what Kelvin is. It is that scale. It measures that. So if you go all the way down to 0 Kelvin, you have absolute 0. And I threw a little video on there on absolute 0, kind of what it is. Basically, it is a complete absence of energy. Now, there's some theoretical stuff that changes it a little bit, but basically it is a complete absence of energy. And so when we do our problems next week, okay, it'll actually be 2 weeks when we'll do a temperature one. Okay, so next week we'll talk about Boyle's law, which is the relationship between pressure and volume. So the temperature one will come back in a couple weeks, but whenever we solve a problem using temperature, we have to use Kelvin, because otherwise 0 is not a true 0, right? 0 would be like saying I have no gas left, but it's in the middle, okay, of your tank. So your standard values of temperature, we have 0 Celsius and 273 Kelvin. So I'm going to come down here real quick, and I'm going to show you how do you convert. I'll go back up to do the mole thing in a minute, but how do you convert from Celsius to Kelvin? It is super duper duper easy. All you have to do is add 273, right? So if I give you a temperature in Kelvin, say 100, and I say, or I give you a temperature in Celsius, and I say, what is that in Kelvin? All you do is you take your Celsius temperature, 100, you add 273 to it, and you get 373. Okay? 200 plus 273 is 473. No matter what temperature I give you in Celsius, all you have to do is add 273. So even if I had like negative 100, okay, what does that equal in Kelvin? If I could type, what does that equal in Kelvin? What do I have to do? Add 273, right? So negative 100 plus 273 equals 173. That's it. So negative 100 degrees Celsius, right? Let's make this correct here. So cut paste, boom, boom. Whoops, that screen just moved on me. That wasn't what I wanted to happen there. But you get 173 Celsius. Sorry, that was longer and that was a waste of your guys' time. And I'm sorry, but I wanted to show you, you can even have like a negative number there and it doesn't matter. All right, so converting to Celsius to Kelvin, add 273, that's it. All right, and I know I'm going fast here, but this is kind of our reality right now. All right, so now let's look at this thing called a mole. All right, so a mole is a unit of quantity in chemistry. Just like a dozen is how many? If you have a dozen eggs, how many eggs do you have? 12, right? So if you have a mole of something, and this is used to measure things that are really, 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 really small, like atoms and molecules, you have 6.02 times 10 to the 23 of that. And you're saying to yourself, okay, that's probably a lot. How much is it? Well, if you're looking at it, here is 100 million, right? That's 100 billion. Now you're in the trillions, quadrillions, centillions, hextillions. So it's a lot. And one of the videos I put up there is the mole song, and it's like kind of talks about if I had a mole of pennies or if I had a mole of marshmallows, how many would I really have? And the abbreviation for mole is really cool here. It's MOL, so it doesn't really save you a lot. It just saves you the E if you want to abbreviate. But so a mole is a unit of quantity. What you need to know with that? Not a lot, just that it exists and it's a unit of quantity. I won't ask you anything about 6.02 times 10 to the 23rd. It's just icing on the cake if you remember that, okay? So again, this week, what do you need to remember? You need to know these units and be familiar with these units. What is volume? The amount of space something takes up. What is pressure? What is temperature? Can I convert from Celsius to Kelvin? And what is a mole? Because as we go forward next week, we're going to start talking about how these variables interact with each other and affect gas laws. Okay? All right. Nothing super exciting this week. I'm sorry. Next week, I think will be a little bit better. We'll get you guys doing some math. I know you're excited about that. All right. And that's all I got for you today. All right, guys. Stay healthy, and I'll see you soon.